The three laws that we just learned, Boyle's law, Charles' law, and Gay-Lussac's law, can all be combined into one law which is much more convenient to deal with, and we call that the combined gas law. And we find that when we use the combined gas law, which is written down here, we don't need to use any of the other gas laws. For example, with Boyle's law, we said temperature was constant. If temperature is constant, then there is no T1 and T2, it's just T. And we can just multiply both sides by T, and away it goes. It simply drops out of the equation. The same idea, for example, with Gay-Lussac's law. If volume is constant, there isn't a V1 and a V2, it's just V. And so dividing both sides by V takes the volume completely out of the equation. So ultimately, we can discard all of those laws and simply use this one for now. Let's go ahead and work through an example here. And I'm going to go ahead and switch to my notes view. So here we have a problem where we're being told that 72.6 liters of a gas is at a temperature of 36 degrees and 0.872 atmospheres. So these are our initial conditions. So let's go ahead and label those. So this is the starting volume. Here we have the starting temperature, but it's in Celsius. So we're going to need to change that to Kelvin. And this is the starting pressure. It's heated to 50 Celsius, and that would be the new temperature, and that also needs to be converted to Kelvin. And it expands to 87.5 liters. That is the new volume, V2. We would like to find the pressure under the new conditions, and that would be P2. So we're going to start here with the combined gas law. So this was P1 times V1 over T1 equals P2 times V2 over T2. The unknown is P2. So we'd like to get that by itself, and we can do that by multiplying by T2 over V2 on both sides. By doing this, that allows us to cancel T2 and cancel V2 on the right side of the equation, and leaves us with P2 by itself. Switching the sides, I'm going to say that P2 now equals, and I'm going to put these in order with the ones first. So we have P1 times V1 times T2 in the numerator. And in the denominator, we have V2 times T1. I'd like you to make an important observation here. It will never be the case that all the ones will be on the same side or all the twos be on the same side. So don't be tempted to go, oh, I'm wrong, and switch the ones and the twos. That simply cannot happen through algebra. So don't do that. Don't try to make the equation pretty. You just want to leave it algebraically correct. Before I stick any numbers in here, I'm reminded that I need to convert my temperatures to Kelvin. So if T1 is 36 Celsius, we need to convert that to Kelvin by adding 273. And that will give us 309 Kelvin. We need to do the same thing with T2. So we have 273 plus 50, and this gives us 323. And the units are going to be Kelvin. And now we're ready to put numbers into the equation. So we just need to read them from the labels at the top. So P1 is 0.872 atmospheres. And please do put in your units. I need more room here. V1, 72.6 liters. T2, now be very careful, because even though people will often get this equation right, they still will put T1 up there, so make sure you get the right number. T2 is 323 Kelvin. V2 is 87.5 liters. And T1 is 309 Kelvin. What can we cancel? We have liters over liters, and we have kelvins over kelvins. So this leaves us with only atmospheres. Going into our calculator, we have 0.872 times 72.6 times 323. Now be careful with the divisions. Divided by 87.5, and again divided by 309, unless you put the whole denominator in parentheses. And this gives me 0.756. And the unit is atmospheres. Something very important to notice about problems involving the combined gas law. There are always going to be duplicates in the type of measurements. So we have here two different volumes. We also have two different temperatures. When we talk about the ideal gas law in a moment, that will not be the case. You'll typically see one value for volume, one value for pressure, one value for moles or temperature. So when you see two of these, that should be a sign that the combined gas law is the equation that you want to use. The next law I'm going to discuss is sometimes actually called a hypothesis instead, but Avogadro's hypothesis, same Avogadro that gave us the number, gives us one of the most exciting statements there is about chemistry. I don't know if you'll find it exciting, but I find this tremendously exciting. And he found that equal amounts of gases occupy equal volumes under the same conditions. Now, the problem here is that you can't see the really exciting part about this, because there's a word that's left out, and that is that equal amounts of different gases, it doesn't matter what the gas is, will occupy equal volumes under the same conditions. So what this is going to do is really simplify our treatment of gases when we're dealing with calculations. Remember in the last chapter when we were having to consider different amounts of reagents reacting with one another, we had to convert from grams to moles. Well, it's going to turn out that that's not really a problem with gases, because once we know their volume, it doesn't matter whether it's 20 grams per mole or 40 grams per mole or what have you. They're going to occupy the same volume under similar conditions. And in a moment we'll see a value that's going to be very important for this. So as I said a second ago, I usually call that last part Avogadro's hypothesis. And then this next part is really Avogadro's law. We're going to add one more important parameter, and that is the parameter n. And n stands for the moles of a gas. So we have a relationship between moles and volume, and it is probably going to be the most obvious of them, and that is the more gas you have, the more space it will take up, so long as we are holding our temperature and pressure constant. The container has to be one that can expand in this kind of a case, like a balloon. So what we see here are volume and amount in moles. So if we don't like the word amount, you can just say volume and moles are directly proportional. If you double the moles of gas, you will need twice as much space, so long as temperature and pressure are held constant. And so this gives us this new equation here. So V1 over N1 equals V2 over N2. If we review all of the laws that we have talked about here, all of them were directly proportional except for Boyle's law. So pressure times volume is a constant, but all of the others were division problems. Putting all of this together, we can come up with yet another law, one that's critically important to us, and that is the ideal gas law. And so what we can find here is, in contrast to all the laws we've just studied, is we now are going to see a law which allows you to find parameters under just one set of conditions. We don't have to look at a before condition and an after condition. So it will be fundamentally different in that way. And it will just show us how these are going to work. And to just explain what this is going to do, what it's going to do is it's going to allow us to say that if I know any three of these, pressure, volume, temperature, or moles, if I know any three of them, I can always find the fourth. So the equation for the ideal gas law is P times V equals N times R times T. And R is a constant, and we call that the universal gas constant. Normally, I give these to you, so it's not a value that necessarily has to be memorized. The units are kind of ugly, but let's see if we can understand why. If you were to try to get R by itself, you would have to divide both sides by N and T. So R would equal PV over NT. And so the units here would be in the numerator at pressure times volume, so volume times pressure, liters times atmospheres. And then in the the denominator, we have moles times Kelvin. Now, while in the other laws you could use any pressure unit you wanted and any volume unit you wanted, that's not going to be the case here. When we're using PV equals nRT, if we're using this version of R, we need to make sure that these are the units we have for all of the values we're going to put in. And if they aren't, you just convert to these units. So as I mentioned a moment ago, if you know any three of these, you can always find the fourth. I don't include R in that because R is always known. It's a constant. So let's try a problem with this, and again I'm going to switch to my notes mode. Now this next problem, although it might initially seem like just any other problem, is a very important one. It's going to give us a value that we can use over and over when we're dealing with gases. It turns out that many of the different gas parameters and experiments are conducted under a certain set of conditions called STP. And when we say we are at STP, that means we are at 1 atmosphere and 0 Celsius. And the reason for being at 0 Celsius is because that would be the temperature of ice. We could just put all of our containers of gases in ice, and that would allow keeping the temperature constant to be a pretty easy thing to do. So let's see what this question is asking. It says, what volume is 1 mole of a gas expected to occupy at exactly 1 atmosphere and exactly 0 degrees Celsius? And I want to give that volume to 3 significant digits because all of these numbers are exact. So the unknown here is going to be volume. Volume is unknown. We have 1 mole. We have 1 atmosphere of pressure. And this is our temperature, but we need to get it to Kelvin. So 0 Celsius would be simply 273 plus 0, which is 273 Kelvin. Please notice there is only one n value, one p value, and one t value, which is going to strongly suggest to us that we need to use the ideal gas law and not the combined gas law, where we would have had 2 temperatures or 2 pressures. So if we want to find volume, we just start off with PV equals nRT. To get volume by itself, we're going to divide both sides by the pressure. Incidentally, you want to practice doing this for all of these so that you can rewrite the ideal gas law with any of these variables on their own. So now the left side allows me to cancel out the p's so that I come up with a new form of the ideal gas law. V equals nRT over P. Now we just need to stick numbers in and units. So N, we said 1 mole. R is 0.0821 liters times atmospheres divided by moles times kelvins. The temperature is 273. And the pressure we said was 1 atmosphere. Canceling units in this case might seem a little bit tricky. But ultimately here we have a fraction in the numerator. And so what that's going to mean is that the liters and the atmospheres are essentially in the numerator and the moles and the kelvins are in the denominator. So that means that moles and moles can cancel, kelvins and kelvins can cancel, and atmospheres, which is in the numerator of the numerator, cancels with the denominator. And this leaves us with only one unit, liters. And when we carry this out, we get a value that I have memorized because it's so useful, and that is the value 22.4 liters. Now you'll notice here I said of a gas. I was not being specific. I didn't say nitrogen, oxygen. It doesn't matter. This applies to any gas which we call an ideal gas. While no gas is truly ideal, most of the gases that we are going to encounter will very much behave like an ideal gas and follow this law. So you should always assume that if we're talking about a gas, that it will follow the ideal gas law. So we can write this out in a statement. If we wanted, we would say that 1 mole of any gas at STP, and STP, remember, is 1 atmosphere, and 0 Celsius, where 0 Celsius is the same as 273 Kelvin, occupies 22.4 liters. Let's look at another problem. So let's suppose that we have a balloon that contains natural gas, methane, and its volume is 7.25 liters. Let's make a note of that. Its pressure is 754 millimeters of mercury, and here is its temperature. I'd like to know how many moles of methane that is. So moles is N. And I want to know how many grams that is, which is the mass, which is not in the equation. So I'll have to find that using the methods that we learned in Chapter 5. Are we okay to go? No. Pressure is not in the right units. We said it needs to be in atmospheres for using the ideal gas law. So let's convert the pressure first. So we have 754 millimeters of mercury. We need millimeters of mercury in the denominator and atmospheres in the numerator. Remember, the equation told us that 1 atmosphere is equivalent to 760 millimeters of mercury. So 754 over 760 is going to be very close to 1. In fact, I think it's 0.993. Let's check. 754 divided by 760 is 0.992. So we want to know first how many moles we have. So looking at the ideal gas law, we have PV equals nRT. N is what we want to get by itself. So we want to get rid of RT, so we can divide both sides by R times T. And so the R's cancel on the right and the T's cancel. And that gives us another form of the ideal gas law. N equals PV over RT. We just now need to put the numbers in. So P we saw was 0.992 atmospheres. Again, please write out the units. The volume is 7.25 liters. R is 0.0821 liters times atmospheres over moles times Kelvin. And the temperature is 296.4 Kelvin. To make the units a little bit simpler, we might want to remember that when we divide by a fraction, that's the same as multiplying by the reciprocal. So let me just go ahead and do that. Let me just bring this whole set of units out. I'll cancel them out in just a minute. So the reciprocal would be moles times kelvins over liters times atmospheres. So I've just brought that out, so I don't need this anymore. And now it's easier to cancel the units. So we have atmospheres over atmospheres, liters over liters, kelvins over kelvins, and the units that we are going to be left with are moles. Before I put this in the calculator, let's look at significant digits. None of these has fewer than 3 significant digits, so we're going to want 3 significant digits on this problem. So I have 0.992 times 7.25 divided by R, 0.0821, divided by 296.4. And this will give me 0.2955, which rounded to 3 significant digits is 0.296 moles. So that's the first part of our problem. Now we want to know how many grams this is. Now think back to the last chapter. We know how to convert from moles to grams if we can find the molar mass. So we want to find the molar mass of methane, CH4. So there's one carbon, so that's going to be, all of these are going to be grams per mole. I'm not going to write it down over and over. So it's 12.01 grams per mole from the carbon, plus 4 times 1.008 grams per mole for the hydrogens. And this gives us 16.04 grams per mole. So now to convert from moles to grams, we're just going to use this relationship here. So we have 0.296 moles of methane, CH4. And this is for every 1 mole, so in the denominator is 1 mole of methane. That would have a mass of 16.04 grams. Moles cancel. And we now have grams. So this is 0.296 divided by 16.04. Excuse me, times 16.04 is 4.75. Grams. This is very powerful because at this point, if we wanted to, we could start doing calculations with the moles, just like we did in Chapter 5, for gases. We can look at how many moles of a gas reacts with another mole of other gases. We are not going to go ahead and do that at this time, though. Instead, we're going to look at one more important law. The last law that I'm going to talk about may initially seem to be fairly complicated, but it's not. It's actually, in many ways, the simplest of all of these laws, and it is Dalton's law of partial pressures. So if we're going to have a law of partial pressures, it's important that we know what a partial pressure is. So this concept applies to mixtures of gases, with air being the most common mixture that we will deal with. So it turns out that every gas, if we were to separate it in a mixture, can be thought of as exerting its own unique pressure. And I want you to imagine that because we said the pressure comes from the collision of each of the gas molecules. If in a mixture of, say, 3 gases, we look at only the collisions of the first gas, that would be the partial pressure from that gas. And then if we only looked at the collisions of the second gas, that would be the partial pressure of that gas. So it just means we're separating a mixture out into its components and looking at the pressure from each of those individual components. So Dalton's law of partial pressures is very simple. It says that the total pressure of a mixture is the sum of the partial pressures. So for example, if we're talking about air, there are many gases in the air, the most commons being nitrogen, oxygen, argon, water, and carbon dioxide, and there are others out there. But if we just look at these gases here, the total air pressure is just the partial pressure of the nitrogen plus the partial pressure of the oxygen plus argon, etc., all the way through here. So mathematically, we can write the equation like this. Say that we have only one gas. Then that would be gas A. Then the total pressure would just be the same as the partial pressure. That doesn't make much sense, but that's because we don't have a mixture if we only have one gas. Let's say we have two gases. If we have two gases, the total pressure would just be the partial pressure of the first gas plus the partial pressure of the second gas. And if there are three gases, you see we would go A, B, C, and if there were four gases, A, B, C, D, and we could just extend this out as far as we need to. It's just the sum of all these partial pressures that is the total pressure. And this is the notation that we use for partial pressure. So if the gas, for example, was nitrogen, we would write P and then the formula N2. For oxygen, we'd say PO2, or we might write the word oxygen. So ultimately, there's just as many terms on the right side as there are gases in the mixture. So I'd like to do an example, and this is probably the easiest problem in the entire class. I'm going to go ahead and switch to my notes view one last time. So let's say we have a mixture of noble gases, argon, neon, and helium. That's going to be nice here because none of these will react with one another, so their composition will stay the same. We're putting them all in a 40-liter container, so there's the volume. The total pressure of the three gases is 1.45 atmospheres. So let's write that as P total. It is 1.45 atmospheres. Argon and neon each have a partial pressure of 0.65 atmospheres. So the partial pressure of argon is 0.65 atmospheres. And the partial pressure of neon is 0.65 atmospheres. And we want to find the partial pressure of helium. So, in other words, the unknown is PHE. So, the equation that we're going to use here to find these partial pressures is Dalton's law of partial pressures, which will say that P total equals the partial pressure of the argon plus the partial pressure of the neon plus the partial pressure of the helium. You will note here that we don't use this volume at all. It's just extraneous information. Since we're trying to find the partial pressure of helium, we could rewrite this equation to subtract these two terms out. I'll just do that a little bit later. Let's just substitute numbers for this one. So right now I have 1.45 atmospheres, that's the total, equals 0.65 plus 0.65 plus the partial pressure of helium. And if you add these together, that's 1.30. So the partial pressure of helium, just subtracting 1.30 from both sides, is 1.45 atmospheres minus 1.30 atmospheres is 0.15 atmospheres. So we notice all three of these values add up to the total pressure. That is going to be the end of the videos for Chapter 6 on gases. The next topic, covered in Chapter 7, will be solutions. Thank you.